Part A of question 9 asks us to find the rate equation for this reaction from these data. So when you get a bunch of initial rate data like this, what you need to try to find are two experiments where only one of the concentrations changes and everything else is kept the same. And you can see 1 and 2 do that because you've got the same concentration of carbon monoxide, but the NO2 concentration has increased and the rate has also changed. So by comparing what factor that changed by with what factor that changed by, we can get the order of reaction for NO2 because we kept the CO the same, so the CO is not going to affect the rate change. Now, usually you get nice comfortable factors like ×2 or ×3. In this case it's not, it's ×1.8. Okay, so you just do 5.4 divided by 3, it gives you ×1.8. But that doesn't matter because you just analyse it in the same way. If this was 0 order, the rate would stay the same. If it was first order, it would change by 1.8. In reality, 14.6 divided by 4.5 is ×3.24. But of course, you can work out what that is because you just say, well, if it's second order, it should change by 1.8 squared. And if you do 1.8 squared, you indeed find that it's that. Okay, so it's ×1.8 squared. And that means that it's second order for NO2. Now, again, in an ideal world, what you then look for is a pair of experiments where the only thing that changes is the CO concentration, and then we could do the same thing to get the order for CO. But there is no such pair of experiments, because you can see the only one that has a different CO concentration is experiment 3, but then the NO2 concentration is different from both of these. But we can deal with that because we already know what the order of reaction is for NO2. So the easiest ones to compare are 1 and 3, but you could do it with 2 and 3 if you wanted. But if we look at that, that was doubled, okay, from 6 to 12. This went up ×4, from 3 to 12. And then we just look at what happened to the rate. Now if we look at, first of all, the NO2, because we know what effect that should have. Okay, so NO2 increased ×4 when we're comparing 1 and 3. And that means that the rate should increase ×4 squared, because we know it's second order for NO2, we've just worked that out. So the rate should increase ×4 squared due to NO2. And then the question is, how much more does it change after that? Okay, so we just work out, therefore 4.5 ×4 squared is 4.5 × 16, which equals 72.0. And that actually is what the rate is. In other words, the fact that we then changed carbon monoxide as well made no difference. The rate change is entirely explained by the NO2 concentration. So that means that the rate change is entirely due to NO2. And the fact that we doubled the carbon monoxide concentration made no difference, and that means that it's 0 order for CO. Okay, so you've got to do the explanations. You can't just write down second order for NO2, 0 order for CO. They will think you guessed. So you need some kind of explanation like this to justify those. And then the question actually asks for the rate equation, so make sure you don't leave it at that. You've then got to put those together and write down your rate equation, which is rate is equal to K times NO2 squared. If carbon monoxide is 0 order, you just leave it out. You don't put it as CO to the power 0. I mean, I guess you could do that and they would probably give you the mark, but if it's 0 order, it means it doesn't affect the rate, so you just leave it out, and that's therefore your answer. The next job is to find the value of the rate constant. So we've got our rate equation. What we need to do is just rearrange that to make K the subject. So you can see we've just got to take the NO2 squared term and move it over to the other side. So as always, it just slides diagonally across. So we get rate divided by NO2 squared is equal to K. And then we can choose any one of these rows and just plug the numbers in, and they would all give the same answer, because that's the point about the rate equation. So if we just choose the first row, but as I say, you could use any of them. So the rate, now this is where you've got to be really careful, because you can see from the column headings that both the rates and the concentrations have been divided by a power of 10. And therefore, to restore that to its original value, you've got to multiply by that power of 10. So you've always got to check, every time you have a data table, every time you have labelled axes on a graph, you've got to check for those powers of 10, because that's a very common thing. So the rate is not just 4.5, it's 4.5 times 10 to the minus 4. And the NO2 concentration, again, is not just 3, it's 3 times 10 to the minus 3. And don't forget that it's got to be squared. Okay, because it's NO2 squared, and if you work that out, it comes out to be 50. So numerically that's the answer, but it needs a unit. With rate constants, the best thing to do is learn the recipe rather than have to work them out. So the recipe is that if Y is the overall order of reaction, and the overall order means the sum of the individual orders. In this case it's just 2 because we've only got NO2. But if there were other substances there, you would add up the individual orders of reaction to get the overall order. But in this case it's just going to be 2. Then the units of K are moles to the 1 minus Y, dm to the 3y minus 3, and then seconds to the minus 1, or it could be minutes to the minus 1. You've always got to check that. You know, it depends on what the data are that you're given, but in this case, seconds to the minus 1. So if Y is 2, that gives you moles to the minus 1. 3 2s are 6 minus 3 is 3, so moles to the minus 1 dm cubed, second to the minus 1. So it's very easy, but you've got to make the effort to learn that little recipe to get the units of the rate constant. Part C wants us to propose a mechanism which is consistent with the overall reaction equation, which is that, and with the rate equation, which is that. So the golden rule, remember, is that the rate determining step has numbers of each substance which match their orders of reaction. That's the golden rule that you've got to learn. So we've got to have a rate determining step which involves 2 NO2s, because it's second order for NO2, and no carbon monoxide, because it's 0 order for carbon monoxide. You've got to learn that relationship. So by far the easiest way is to make the slow step the first step. If you don't do that, it's a bit more complicated, because you have to add up steps and stuff. So just keep it simple. Make the slow step the first step, and then have a fast second step. So it's second order for NO2, and that means that there must be 2 NO2s in that slow step, because the slow step is the rate determining step. That's got to go to something. The carbon monoxide has got to come in the second step, so that's going to come in here. Now we've got to make up the details, and the rest of this, there is more than one possible answer. But the simplest thing is to think, well, overall actually only one NO2 reacts. So if 2 get used up here, the simplest way to sort it out is to suggest that one of them gets regenerated in the second step, so that although 2 are used up overall, we get one of them back. So overall only one NO2 is used up, and that will give us 1 NO2 reacted overall, as well as 1 CO, so that will work for the left hand side. So what could be here? And the answer is, well, pretty much whatever you want, but the simplest thing is to see if we can make any of the correct products in this first step. And the answer is, of course, yeah, we can make an NO, because we've got the atoms for that. Obviously can't make CO2 because we haven't brought the carbon in yet. So if we have NO, what does that leave? Well, 2 NO2s is 2 nitrogens and 4 oxygens. We've used 1 nitrogen and 1 oxygen, so that would leave NO3 as the other thing that was formed. So we want this because it's there in the final equation, so that's fine. We don't want this because it's not there in the final equation, so we just feed it back in there. So we're proposing it as an intermediate, which is then used up in the second step. And that will then give us the NO2 back, and it will give us our other product that we need, which is CO2. You can check that it's right by adding everything together, because obviously there's scope to get a bit fuddled as you go through this, so you can just always check by adding the 2 steps together. So you get 2NO2 plus CO plus NO3, adding up all the left hand side stuff, and then again adding all these up, you get NO plus NO3 plus NO2 plus CO2. So it looks really messy, but there's lots of simplifying to be done. First of all, the NO3 cancels out because it's there on both sides. Secondly, we've got 2 NO2s on the left, but one of them's still there on the right, so that cancels out and that goes down to just 1, and that leaves us NO2 plus CO goes to NO plus CO2, which is the correct overall equation. To complete the answer, it actually said make it clear which is the rate determining step, and you can see we haven't actually written that down. We've said slow and fast, but they may not understand that slow necessarily means rate determining, so you need to write down that this is the slow step and therefore is the rate determining step. So make that explicit, because that was asked for in the question. So make sure you explain the slow step as the rate determining one. Okay, so that approach to mechanisms is important. The key relationship to remember is that the order of reaction is equal to the number of things reacting in that slow rate determining step. And then you just make everything else fit around that to give you the correct overall equation.